Welcome to 6502 Assembly Language Programming. In this video, we'll write our first lines of code. But before we can write any code, I need to introduce you to the 6502 microprocessor. It is an 8-bit microprocessor, which means it handles 8 bits of data at a time. It has 3 general purpose registers, all 8 bits, an 8-bit stack pointer, a 16-bit program counter, and a program status register. It supports 56 instructions and can address up to 64 kilobytes of memory. Here is a block diagram of the 6502 microprocessor. On the left is a depiction of the register file. Just going through the registers in turn, the A register or accumulator is the target or the source of data for most arithmetic operations. The X and Y registers have a limited arithmetic capability but are used for advanced memory addressing. The PSR or program status register contains information about the last arithmetic operation performed. It answers questions like, was the result 0? Was the result negative? Was there an arithmetic overflow? That sort of thing. The stack pointer indexes the stack area and is used to contain temporary variables, but most importantly, the return address of the last subroutine call. You'll learn about subroutine calls later on. The PC, or program counter, is the only 16-bit register, and it points to the next instruction to be executed. On the right of the diagram, you see a depiction of the address range of the microprocessor. At the very bottom or top, depending on how you look at it, of the address range is the base page, addresses 0 through FF hexadecimal. This area is very important because when you put variables there, you can address them with only an 8-bit address. This area is heavily used. The rest of the address space must be addressed with a 16-bit address. And this makes instructions that do that 8 bits longer because they have to have a 16-bit address encoded. Now, the 16-bit address bus is the mechanism that communicates the address of data to be manipulated. And the 8-bit data bus is where the data is transferred to and from memory or from the CPU to and from I/O devices. So now let's get started. We're going to go to the 8bitsand1byte.com website and then navigate to course source files. And we'll write our first lines of code. So here we are at the 8bitsand1byte website. We're going to navigate immediately to the course software by clicking on the Learn 6502 link and then clicking on the course source files link. Here on this page we have 2 choices. We can see the completed exercises where you have my solution to each exercise, or you can go solve them yourself. Let's click on that choice. I want to give you a quick introduction to the 8bitsand1byte IDE. The IDE has 3 principal tabs. The Source tab, which allows you to edit your source code. The Files tab, which allows you to save your work and perhaps reload it later. And the Run tab, where you can run and debug your code. The Run tab uses the DASM.js assembler to generate the object code and it uses the Atari simulator to run the code. Atari provides a very good simulation of the Atari 2600 game system. The Run tab has three principal windows: the DASM.js listing window, the debug window on the right, and the Atari 2600 simulator at bottom. Going back to the listing is a very traditional tool for assembly language programming. It mainly serves to show you where variables and code reside in memory. Let's walk through this window. Line numbers on the far left aren't part of the listing, but are there to allow you to set breakpoints. So for instance, if I click on line 77, I get a little red glyph there, and execution stops at that point. And I can examine things in memory and in the CPU registers. If I click on that spot again, it removes the breakpoint, and I can resume execution. The column next to the line numbers contain addresses, and these are addresses of the generated code, as in this case, or perhaps of memory that's allocated to variables. To the right of the object code is the 6502 source code. At the bottom of the listing pane are 4 buttons that control execution during break state. Resume, as the name implies, resumes execution of the program, and it will run until it hits the next breakpoint. Step over, clicking step over executes one instruction. If the instruction is a subroutine call, it'll execute the subroutine call as if it were one instruction, and the next instruction you see will be the one immediately after the subroutine call. Step into executes one instruction, and if that instruction is a subroutine call, it will step into the subroutine call. The next instruction you will see will be the first instruction of the subroutine. Step out will step out of a subroutine. The next instruction you see will be the one immediately after the subroutine call. Let's set a breakpoint and look at the debugging pane. The debugging pane has 4 buttons at the top and 3 at the bottom. The buttons at the bottom relate to game development, and we'll visit them later in the course. At the top are 2 zoom buttons: zoom in, zoom out, and buttons to select the log and CPU panes. The log pane is a bit of a catch-all place for information from both the DASM.js assembler and the debugger. DASM.js will put assembly success or error messages there. The debugger will display the CPU state and the contents of the Atari 2600 memory. The CPU pane displays the CPU state but has 2 additional formatting options. You can select the display base for the general purpose registers. Right now it's base 2 for A, X, and Y. Now it's base 10. Now it's base 16. And back to base 2. Clicking header will remove the column headers on each sub-window, if you find that more readable. Removing our breakpoint, clicking resume, let's go look at the Atari simulator display. It consists of the output screen and a rendering of the Atari 2600 console. These buttons are functional to the extent that the software that's running listens to them. let's go back to the source tab and access the ex0.asm file. As you can see, you can pick the file you're editing by selecting it on this pull down. I also want to highlight this C solution button. You can click on that and it'll load up my solution to this exercise. So the things I want to point out here are, one, the semicolon, which is the introduction of a comment. Every line starting with a semicolon is a comment. The assembler ignores the content of these lines, and so you're free to write anything you want here in terms of documentation or whatever you might think you want to know later. And here I'm using it to communicate the requirements for a successful completion of this exercise. Now, the exercises, each exercise is a subroutine. A subroutine is a named sequence of instructions that can be called repeatedly, but is also useful for isolating that sequence of instructions so that you can code them in isolation without having to worry about surrounding instructions. Now I want to talk about the protocol for solving an exercise. Having read the instructions, you'll code your solution and then change this LDX # not implemented to LDX # implemented. Now, since we're talking about LDX, I need to tell you what that is. That stands for load X, and it transfers data from memory into the X register. Let's use our instruction reference to find out about the LDX instruction. Now, I have provided a link to this web page in the description below. It's an excellent instruction reference for the 6502 and rather better than the other ones out there, I think. So, at the top of the page here, we have a list of the 6502 instructions. We're going to click on LDX. As you can see, there's quite a bit of information about the LDX instruction. It tells you what it does, loads a byte of memory into the X register, and it tells you how it affects the flags. The flags are individual bits in the PSR that we've talked about before. In this case, it sets or affects the 0 flag and the negative flag. And these flags are either set to 1 or 0, depending on whether or not the result is 0 or the result is a negative. Below that, we have the addressing modes that the LDX supports. The two most important addressing modes are immediate and zero page. In immediate addressing, the data loaded into the X register is in the instruction itself. This is appropriate if the data can fit into a byte. In zero page instruction, the address of the data fits into a byte and is used to address the first 255 bytes of storage. This is great for the Atari 2600 since all the RAM in the system is within the base page. Let's look at the Run tab and see if we can figure out why our exercise isn't working. Now, for a quick guided tour of the Run tab screen. In this panel here, you have the listing. The listing is a product of the assembly process, and it mainly serves to show where the instructions are and what code is being generated. So I'm just going to scroll back and forth until I can find our EX0, and here it is. So what we're going to do is set a breakpoint here by clicking on the line number to the left. As you can see, that immediately changes the window to the right. This window on the right contains debugging information. This area here is the entire area of RAM for the system. This is all the RAM in the system. It's only 128 bytes. So hats off to all the thousands of video game programmers that manage to produce significant works with this small amount of memory. Okay, well, let's have a look at things. So we can see that our job is to take the value from param underscore 0 and store it in output 0. So let's look at where this stuff is. Here we have param underscore 0, and you can see that it is at address 80. Oops, sorry, didn't mean to scroll. It is at address 80, which is right here. And then we're going to store that in output 0, which is at address 8 alpha, which is, we'll have to count. This is there's 4 bytes here, so that means it's 8 bytes here, and it means it's this byte right here. So it says 0B F3. Here, I'm going to make that bigger. 0B F3, and then 00. So what we should have done is move this this value here, this 14 hexadecimal, from there to this location over here, and we haven't done that yet. So that is why our exercise is failing. Now, I encourage you to take a moment and see if you can complete this exercise successfully. I'll give you a few moments to do that if you want to pause. Welcome back. So let's go ahead and finish our exercise. I'm going to go down to EX0. And so I'm going to code, oops, tabbing just is not quite correct here. I'm going to code LDA param underscore 0, and then SDA output 0. Now, each line of assembly language consists of a label and then a directive like subroutine or an instruction like LDA or STA. After the instruction, there is usually a parameter, not always, but usually. And this tells what memory location or register is involved in the instruction. So here I'm saying load the value in param 0 into the A register, and then in this instruction I'm saying store the value in register A to output underscore 0. Okay, let's have a look at our solution and see how it works. Here we are back in the 8 bits and 1 byte IDE, the run pane, and we're going to step through the first instruction of our solution, the LDA param 0. You may recall param 0 is in the base page, so we are using base page addressing, and the assembler figures this out, you don't have to, for the instruction. And this 80 in the instruction is the address of param 0. Now that's true of the output variable too. Output 0 is also a base page variable, and here's the address of that, 8A. So let's execute param 0. We're going to click the step over button, and step over executes the next instruction. The over part only has to do with subroutines, and we'll explain that when we get to subroutines. So we loaded whatever's in param 0, address 80, into the A register. Here's address 80 there. It has 14 hexadecimal in it. And if you look at the A register here, it has the value 14 hexadecimal in it. And we'll we'll step over the next instruction, the store A output 0, and we'll go look at address 8A. That is here, and that now has the number hexadecimal 14 in it. Okay, so I think our solution is working. So let's remove the breakpoint and just let the code run and go and look at our output screen. So here you have a green light saying that our solution worked. This concludes this video. Thank you very much for listening. I hope you enjoyed it and derived some benefit from it. If you have any questions, please ask in the comments below, and I'll do my best to answer. And it would really help me if you would like and subscribe. Have a great day.